So now we are going to study how to use Gauss law to calculate electric field. It is section 2.2 of the textbook. So earlier we studied how to use Coulomb's law to calculate electric field. It is very easy when we calculate a point charge or collision of points based on principle of superposition. But when it's distribution, the calculation become more complicated. So as engineers, we desperately want to avoid very complicated calculation. So Gauss law will help us to calculate electrical field as an alternative method. It's especially easy when we have distribution of charge that is a constant, so that we can take the density, the charge density outside of the integral sign. But before we get into details into Gauss law, let's come back to Coulomb's law first for a moment. So Coulomb's law already tells us everything about electrostatics. So basically, so come back to the earlier question, what is electric field? So we have a source charge, and then we have a test charge. The test charge would feel a force. So if they are of the same sign, then the force will be repulsive. So if they are of opposite sign, they will attract to each other. So the test charge would feel a force. However, the source charge didn't reach out to the test charge to push and pull. It doesn't have an arm to reach out to push or pull the test charge. Yet, test charge felt the force. So in Maxwell's time, Maxwell concluded based on Coulomb's law that there is material that filled the space called ether that's jelly-like. It can convey, the force, so that test charge can feel the force from the source charge. However, Einstein proved that ether doesn't exist. However, we still need to consider electrical field as physical entity that flows, just like water, just like wave on water. That's exactly how we consider electromagnetic wave propagation. So it is wave, it's physical entity that flows. So suppose we have, like a pond, and then we throw a stone into the pond, and then there will be wave propagate toward outside of a region that you observe. So the longer the distance, the lower the magnitude, the wave would decrease over distance. So electrical field can be considered the same way as wave on water. So if you observe like a surface, a closed area, if you can define the total amount of flux that flow outside of the area, then you can determine the property of the stone. So how heavy the stone is, and what is the property of the wave propagate outward from the position where the stone is thrown into. So Gauss law tells us exactly this. So if I have a surface and we can calculate the flux, the electrical field that passes through the closed surface, that flux is determined by the total charge enclosed in the surface. So Gauss law. Okay. So first of all, we need to define a flux. So electric flux is defined by the electrical field that flow across a surface. Okay, that's a flux. And then Gauss law tells us that the total amount of the flux of a closed surface is determined by the total charge enclosed divided by epsilon 0. So obviously, if it's a point charge, we have the total charge enclosed just equal to the single source charge. And if it's a collection of points, then based on the principle of superposition, we have the total amount of charge enclosed equal to the summation of all of them, right? Now, if it's a distribution, we have the density, and we need to calculate integral. So what is dq? So if I have the density, if I have a line charge, we have a density as a function of location. Then line charge is lambda multiply dl. And if I have surface charge, and then we have a density as a function of location, then it's rho dl. And then if we have a space of volume charge, the density is rho as a function of location. I have rho dl. So Gauss law is always true. Gauss law is always true, but it's not always trivial. It's not always helpful to us. It's only helpful to us when we have constant density, where if it's a line charge, it's not a function of the location. It's constant density across the line. So if it's line charge, we have dq equals lambda dl, so we need to do line integral, but the density is a constant. And then we have a surface. Similarly, dq equals rho dA, so we do surface integral. And then if I have volume, we have dq equals rho d tau, so we do volume integral. But the density, they're all constant. That is what we care about for Gauss law. So Gauss law also has a differential form. So for the Gauss law in differential form, we need to go to the fundamental theorem for divergence, which is also called Gauss theorem. So that's very closely related to Gauss law, right? So we need to apply Gauss theorem to Gauss law. So what is Gauss theorem or fundamental theorem for divergence? It is volume integral divergence of the field d tau equals to closed surface integral of the electrical field. So this is a fundamental theorem for divergence, which is also called Gauss theorem. And now based on Gauss law here, we already know the closed surface integral of E. This equals to the total charge enclosed divided by epsilon 0. And now here we have the volume integral. So we care about the volume density here. So if we extend this based on volume density, what we have would be volume integral as well, and then rho divided by epsilon 0 d tau. So here we have the same volume integral. So we can conclude that the divergence of electrical field equals to the charge density enclosed divided by epsilon 0. So this is differential form, and this is integral form. And the integral form is actually more useful for us, because if we know the total charge enclosed, this is a constant here, and then we need to consider, we need to imagine a surface. So this is surface integral, right? We need to imagine a surface where all the electrical field, they are uniformly distributed. So they are all the same over a surface. So if it's a density, so if it's a point charge in the middle, then a sphere surface would have, so every point on the sphere would have the same electrical field. So when electrical field is a constant, we can move it out of the integral sign. And the integral here, the surface integral, is just a total amount of area of the sphere. We're going to look at some examples. Before we move on to examples, let's look at a very important property of electrical field that has nothing to do with Gauss law, but it's very important for electrical field, which is the curl of electrical field. So in order to investigate the curl of electrical field, we need the fundamental theorem of for the fundamental theorem for the curl, which is the surface integral of curl electrical field equals to closed line integral of the field. So how to calculate, how to determine this? So we have, so if we come back to Coulomb's law, and if it's a point charge, we have 1 divided by 4 pi epsilon 0, and then Q divided by R square. And then it's the direction of R, so it's spread out. So now the line integral from a point A to B, we have 4 pi epsilon, this is constant. We have Q, which is also a constant, and then line integral from A to B, 1 over R square dr. This is quite simple. So what we have is minus Q divided by 4 pi epsilon 0, and then 1 over R from A to B. So eventually here we have 4 pi epsilon 0 Q, and then 1 divided by A minus 1 divided by B. Okay, so this is a line integral. But from the fundamental theorem for curl, we have a closed loop. So when the starting point equals to the end point, finishing point, then this would equal to 0. This tells us that the curl of E equals to 0. Okay, so this is quite it does make sense, because the electrical field is spread out, so it has a divergence. Divergence of a vector tells us how a vector spread out, and then the curl of a vector tells us how a vector swirl around a circle. So obviously, electrical field, it doesn't swirl around a circle. So when everything's stationary, electrostatics will have curl of E equal to 0. Look at an example about how to use Gauss law to calculate electric field. So this is sphere Gaussian surface. It is example 2.3 of the textbook. So suppose we have a uniformly charged sphere. The total amount of charge is Q, and the radius is R. Then at a point outside of the sphere, what is the electric field like? So if this is a perfect sphere and it's uniformly charged, then we can imagine there is a Gaussian surface. The same distance R, they will have the same electrical field at all these points. It's exactly like wave on water, where you throw a stone here, and then all the wave magnitude on the circle, they would have the same magnitude. So now if we have a Gauss law, which is the closed surface integral on E, which is the electric flux equals to the total charge enclosed divided by epsilon 0, and we know the total charge is just Q, so this is Q divided by epsilon 0. Okay, and then this thing, if we consider this Gaussian surface, and they all share the same amount of electrical field, so the magnitude of electrical field on this surface, they're all equal, and the direction of electrical field is spreading out. So there's also direction of an area which is perpendicular to the area. So these two have share the same direction. So we can move the magnitude of electric field outside of the integral, and then the integral is just the total amount of area of the sphere, which is 4 pi r squared. So we have E, so this equals this, and then this equals to E multiply 4 pi r squared. Okay, so in summary, this equals this. So I have electrical field equals 4 pi epsilon 0, and then Q divided by r squared, and the direction is spread out, so R. Okay, so now this expression is, so this is the answer, but this expression is exactly the same as Coulomb's law with point charge Q. So if you look at this equation, it's not affected by the value of the capital R. So no matter how big the sphere is, the electrical field outside of the sphere would consider this sphere equivalent to a point charge. So the size of the sphere doesn't affect the magnitude of electrical field. Okay, the second example is a plane charge. This is example 2.4 of the textbook. So suppose we have an infinite plane, and the surface charge density is rho. So what is the electric field? So imagine we have a like a very like a Gaussian pure box, like a pure box, which has a area and a very, very small very small height, and then the box is crossing the area, so it come out a little bit outside on the right hand side of the plane and a little bit outside of the left hand side of the plane. So on the other side, the box is closed. Let me see how to draw this. I'm a terrible drawer. Okay, that will be the other side. Okay, sure, that's possible as a pure box. Here, this is a pure box. And our observation is the area, the face of area is A, whatever the value is, but it must be big enough so that the height here is considered infinitesimally small. So the closed surface would only have total area of 2A. So one face area here and the other one on the other side of the plane. Okay, now we have the Gauss. We have Gauss law that tells us the total flux equals to the total charge enclosed divided by epsilon 0, and total charge enclosed should equal to the surface density multiply area divided by epsilon 0. So there is only one plane, and we observe the area on the plane, which is rho A epsilon 0. And now here the total flux. So both sides we have the same distance, okay, but this is an infinite plane. So what I'm trying to say is the electrical field on the plane outside of the pure box here, the electrical field is constant, so we can put it outside of the integral sign. And total area is 2A because we have one surface on the left hand side, and then the pure box it come out a little bit outside of the left hand side and outside of the outside of left hand side and outside of right hand side. Okay, so we have this equals to E multiplied 2A. So now in summary, I have E equals to sigma divided by 2 epsilon 0, and the direction is perpendicular to the surface, like this, right? So that's the electrical field. This looks very curious as well, because the electrical field here is independent of how far away you are from the plane charge. So no matter how far you go, the electrical field is only determined by the density. So first of all, this is only valid when the plane is an infinite plane. But this calculation is fairly accurate when you stay away from the edges. Another way of looking at this is, for example, you have a plane and you have a surface density, and you have a microscope you observe the plane. So the area of microscope, the observation here is pi r square. And we know from Coulomb's law that the electrical field equals 1 divided by 4 pi epsilon 0 and then q r square. So the electrical field would fall out. So one is like a point charge, but it's kind of proportionate to surface charge because of the principle of superposition. You just consider them like superposition together. But the point here is the magnitude of electrical field would fall out with a factor of 1 divided by r square, and this r square and this r square will cancel each other. So as you zoom out, as you go a little bit further, you'll observe a larger area. But the decreasing, the fading would cancel that increasing area. So that's another way of looking at this. Anyway, this is more accurate when it's calculated based on infinite plane, but it's fairly accurate when you stay away from the edges. So another further example is example 2.5, where you have two planes. Okay, you have two planes, and one is positive charged, another is negative charged. So what is the electrical field like? So there are also two ways of looking at this. One way is if you consider the plane to be perpendicular to this piece of paper. So I have one plane, another plane. One is positive charged, another is negative charged. So from the positive charged plane, we have electrical field coming out. Coming out from here. And then from the negative charge, we have electrical field coming into that plane. So based on this calculation, one is positive charge, one is negative charge. That's already taken care of by the direction here. So the magnitude is the same. So these two, they are of opposite direction. The electrical field would be 0 here. And here the same, they are of opposite direction. The field would be 0. And here, these two will enforce each other. So we have 2 times of this magnitude, sigma to epsilon 0. So in the middle, we have sigma divided by epsilon 0. Okay? That's one way of looking at this. Another way is if we draw a big pillbox. How do I draw this? Okay. Yeah. So this line should go there actually. Anyway, yes. Yeah, just imagine it's a like a cubic pillbox. Okay, so you have this pillbox that come slightly out of this plane and coming slightly out of this plane as well. to the opposite direction. So these two planes are still considered, infinite planes. So the length here is considered small, and the area you observe is here. So for this pure box, you have an area that's positive charged, you have an area that's negative charged. So the total amount of charge enclosed is 0. So here the electric field outside of this side of the plane is 0. And the electric field inside, so on left to the positive charged plane, is also 0. So now if we draw a small pure box only on one plane, so I'm sorry about my drawing, but anyway, consider this is a pure box. So we know the other side, the field is 0. So twice of the electric field would come out from this side. So the electric field on this side would be twice of sigma divided by 2 sigma to epsilon 0. So this is sigma divided by epsilon 0. And then you have a pure box here. And you know the field here is 0, so all the electric field would pass through this surface. So we know the magnitude is like this, so 2 times of this in the middle, but 0 on both sides, outside of these two planes. Hope that's clear.